Hello guys, welcome to Exam List. In this lecture series, we will learn about the cat-bra notation and the commutator relations. Great. Now, so let us take a quick review of what we have studied in quantum mechanics. So we learned about a wave function psi. This wave function psi represents the microscopic particle that has both wave and particle nature. And this wave function psi satisfies an equation known as the Schrodinger's wave equation. Agreed? Then there were other postulates that says that the only interpretation of psi, since psi is complex, so what we did, we saw that psi square was real. Okay, and we connected the psi square which is real to the probability. So this has been discussed earlier. Now, so what is psi square? Now, since psi is complex, so psi square, so whenever you see psi square, just always remember it is psi star psi. Great. So it should be written more properly as mod of psi square. Agreed. Now, then we studied that probability can be represented for a particular distance. So consider you are asking the probability of a particle whether it has reached in position between x and x plus dx. Then this probability is calculated by psi square dx. Okay, so we have discussed this. Then we learned that total probability is always 1. Okay, and the mathematical way of saying total probability 1 is integration minus infinity to infinity psi square dx is 1. Now remember, this is for 1D. This is for one dimension. Okay, till now we have all done everything in one dimension only. So what is psi square? Psi. Okay, remember psi is a function of x. Okay, and then it is written psi, which is a function of x square. It means what? It again means psi star psi. Then we studied about various wave functions. So this is a wave function that represents a free particle which have a unique momentum. Okay, so if there is a free particle whose momentum is exactly known, then what will happen? If momentum is exactly known, then uncertainty in momentum is 0, because the momentum is exactly known, but the uncertainty in position will be infinity. Okay, how do you get this? You know that the product of uncertainty in position multiplied with product of uncertainty in momentum is always h cross by 2. So this is a quantum mechanical relation. So in quantum mechanics, not in classical, in quantum mechanics, if the momentum is exactly known, then the particle cannot be found easily. This happens only in quantum mechanical region where you have small particles. Agreed? So for this wave function, these wave function are called as the momentum wave function or the momentum states. Why they are called momentum states? Because on these wave functions, the momentum operator can act on this wave function and can snatch out the value of p. Okay, that is the momentum out of it. Okay, so what is the operator? So what you can do is, if you apply this operator, which is minus I h cross del psi by minus I h cross del by del x. So this is the momentum operator. So when this momentum operator, you act it on the wave function which is a e to the power I p by h cross x. So when you act on this, okay, if you do a little bit of calculation, you will get a p outside and the entire wave function psi as it is. So what is psi? This part is psi. So you see that when momentum operator acts on the wave function, we get momentum. Agreed? So this is already been discussed. The wave function that you see below, the second one, these are called as the position eigen function or position wave function. Okay, I should not have So why they are called eigenfunction? Because they have a particular eigenvalue. For example, the upper equation is called as the momentum eigenfunction. Why it is called momentum eigenfunction? Because this psi satisfies the relation that when momentum operator acts on psi, you get the momentum and the psi again. So this is an eigenvalue. This type of equation are called as eigenvalue equation. Okay, the functions are called as the eigenfunction. So this is called as the psi is called as the eigenfunction, and p is called as the eigenvalue, and the entire equation is called as the eigenvalue equation. Agreed? So similarly, the lower part, this part, these are called as the eigen function of position operator. For example, on this wave function, on this wave function, only when position operator acts on this wave function, then you get the value of where the particle is. Now according to the equation, you know that we have already discussed about Dirac delta. So the particle is where? The particle is at x naught. Okay, you see again, this is an eigenvalue equation. X naught is the eigenvalue, psi is again the eigen function. Agreed? So this is just typical names. So what is Heisenberg principle says for this type of wave function? See, for this type of wave function, there is no uncertainty in position. The position is exactly known, so the uncertainty in position is 0. Hence the momentum is unknown. The momentum is it may skip to infinity. It means the more and more you confine a particle, the more is its momentum. Let me give you an example. So consider you have a very small circular place, okay, circular potential, where you confine a small particle. Okay, then quantum mechanically, so what classical mechanics says? The classical mechanics says, okay, the particle is in a potential, so what? No problem. But quantum mechanics says no. Quantum mechanics says if you confine a particle in small place, then somehow the particle will have a very high momentum. This is a reality. Agreed? Again, if in quantum mechanics, if you confine a particle in a small potential region, then by virtue of quantum mechanics, somehow the particle will gain huge amount of momentum. From where the momentum comes, that's the different stuff. But quantum mechanically, it will have huge amount of momentum. Then what we studied? Then we have also studied about the expectation value, how we calculate the expectation values. Agreed? So this is what we have studied till now in quantum mechanics. Now, and the last and but not the least, the most important thing is the Heisenberg uncertainty principle that says that product of uncertainty in position with product of uncertainty in momentum is greater than equals to h cross by 2. Agreed? So this is what we have done till now. Suddenly a theoretical physicist comes and he says the following. He says this, hey look, let us introduce a notation called as the Cat-Bra notation. Okay, so he introduces the Cat-Bra notation. It was actually the Dirac who did it. So why the Cat-Bra notation? He says that, hey look, your quantum mechanics contains terms like in something goes from minus infinity to infinity, then you have psi star psi dx. So why to write integration again and again? So let us write this in a symbolic manner. So write this as psi, so that is bra psi and a cat psi combined together. Okay, so bra sign means, so this is the bra psi, okay, and cat means this. Agreed? So this is the bra and this is the cat. Both the bra and the cat form the bracket. That's why the name bracket. Okay. So you can see that he said that, hey, let us use some easy symbols. So this will make life easier. This will make life easier. So what is the meaning? So whenever the psi is on the bra side, it will give you a psi star, and when the psi is on the cat side, it will give you a psi. Okay. So how to write this relation in the bracket notation? So this relation will be psi star. So psi will be in the bra, and there is an operator in between. So let us keep the operator in between, and there is a psi, the real psi. So keep it in the cat position. Now how to write this one? This one will be written as psi star means keep it in the bra, and then keep the momentum operator here, and then you have the psi on the cat side. Okay, these are just notation. So these notations were introduced, and suddenly this theoretical physicist all of a sudden says that if you use my notations and if you use the operator formalism, then there is another mathematical way of writing the Heisenberg uncertainty principle. The mathematical way of writing the Heisenberg uncertainty principle is that when you do the commutation relation of position operator and momentum operator, he said that it is equals to I h cross. So what is the momentum of what is the meaning of this commutation? It means x multiplied with p minus p multiplied with x. Okay. So what the scientist said is that, what the physicist says that instead of using this equation again and again to find your answer, he said use this equation. And he claimed that these two equations are similar to each other. Okay, either you write expectation value, either you write the uncertainty in position multiplied with uncertainty in momentum greater than equals to h cross by 2. He said that that part is same as if you write x operator and the p operator equals to I h cross. So in this way the commutation relation entered the picture. So the entrance of the cat bra notation into the picture is very easy because they are just a style of writing. They just simplify it. Okay, this is just a notation. Okay, this is style of writing. But the amazing thing was the another form of Heisenberg principle. The amazing thing was the commutation form of the Heisenberg uncertainty principle, which was the main thing. So this is something is very important. He said that instead of using this particular form where you are multiplying two standard deviations and you are writing an inequality equation, so instead of writing this, he said that use this commutation relation. So now he claimed that this commutation relation is equivalent to Heisenberg uncertainty principle. Both are same thing. Now the question is, why is that commutation relation represents Heisenberg uncertainty principle? I mean, is that commutation relation so true that instead of using Heisenberg uncertainty principle, we can use the commutation relation? And how come the commutation relation automatically encodes in it the information of uncertainty principle? That will be the subject of next lecture. So what I mean to say is, how did the commutation relation enter the entire picture of what we had of quantum mechanics? Okay, so the moment commutation relation enters the picture, things actually became simplified. The Cat-Brown notation simplified the complex calculation, and the commutation relation gave a new look to quantum mechanics. So instead of using the Heisenberg uncertainty principle, you use the commutation relation because both says the same thing. Agreed? So in the next lecture, we'll see how the commutator relation. So this is encoding the information of Heisenberg uncertainty principle. We'll do that in next lecture.